Page 15, chapter 15. Here we go. We're looking at random variables and discrete random variables and then probability distributions today. Pass that back to Albert. So a random variable is a measure of a quantity which can take on any range of values. And if it's a discrete one, then there's only countable things that could happen. It could happen once, twice. You know, there's certain ones that could happen, but you can count them up to a certain amount. So an example of that is if you roll a dice 4 times, how many 3s could you get? Well, you could get 4 3s if you roll it 4 times. You could get 0 3s if you roll it 4 times. But you could also get 1, 2, and 3. So there's 5 different countable values that you could get. One of the things that we're going to see is this big X equals, and it's going to look funny as far as notation. But the big X equals is what we're looking at. Big X equals here is the number of 3s. So we'll see that later. You could also have a continuous random variable which could take on any value in an interval. So the time it takes for a car to finish a race, well, that could be any second and any millisecond in there. So there's not just a countable amount. A probability distribution, and it works only for the discrete random ones because it has to have a countable amount, is just a list of each possibility and the probability that it occurs. So you take a coin, you flip it twice. Here's our tree diagram. What could happen the first time? You could get heads or tails. And then the second time, you could get heads or tails. So our first branch represents getting 2 heads. Our second branch, a head and then a tail, then a head, then 2 tails. So that's our sample space of tossing a coin twice. So here's our big X equals. We define the big X here as the number of heads that you could get. When you flip a coin twice, can you see that there's 3 possibilities for the number of heads you could get? How many heads could you get if you flip a coin twice? You could get none. You could get 1, or you could get 2. Now, if we go back to our tree diagram, getting no heads, that's your tails, tails. That looks like pi. There we go. Tails, tails. That's no heads. How many times did that happen? Just 1 out of the 4 possibilities. Getting 1 head could happen either heads, tails, or tails, heads. So there was 2 out of the 4. And getting 2 heads only happened 1 out of the 4 times. And we write right here, probability of big X equaling little x. So this notation is confusing looking, to say the least. But what it means, probability of big X equaling little x, is the probability that big X is the number of heads is little x, and little x goes through 0, 1, and 2. So if we pick one of these numbers, this 1/4, that's the probability of big X equaling 2. In other words, that's the probability of the number of heads when you toss it twice equaling 2, which is 1/4. So the first thing we got to sort of grapple with is, what does this notation mean? What does big X equal little x mean? So the big X is what you're looking at. Here it's the number of heads obtained. And the little x are the different possibilities. Either you could get 0 heads, 1 head, or 2 heads. This will always equal 1 because it's all possibilities. And so it always adds up to 100%. So that column will always equal 1. So we have that here. What I just pointed out, the sum of all of those will always equal 1. And for any one of them, if you look at any one in particular, it has to be between 0 and 1. You can't have a probability less than 0. You can't have the probability of something bigger than 0. So now we toss our coin 3 times. So we could quickly draw good thing I didn't decide to toss it 7 times. So we've got heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads. All right. So now if x represents the number of heads, doesn't make sense when you toss it 3 times. You still could get 0 heads. There's a possibility of getting only 1 out of the 3 with heads, possibility of getting 2 out of the 3 heads, and a possibility of getting all 3 of them heads. If we look at 0 heads, that's all tails. That's this one right here. There is a 1 out of 8 chance of that. If we look at getting 1 head, so we go through, it's right here, it's right there, there, and right there. So our possibility for those blue circles, 3 out of the 8. 2 heads, there's 1 there, and 1 there. Possibility of that is 3 out of 8. And getting all 3 heads only happens once, 1 out of 8. Again, this bottom part here, if you add it up, equals 1, because that's all 100% of the possibilities. So try this one. Draw out a sample space and a tree diagram, and then put the results in a probability distribution. And here our big X is the number of green marbles. So if you take out 2 marbles and replace the marbles, draw a tree diagram, and complete the distribution chart. Okay, see how you've done. Got my tree diagram going up and down this time. Probability of getting 0 green marbles. That is the branch of both red ones. 2 out of 8 times 2 out of 8 makes 4 out of 64. Probability of getting 1 red one. Well, we have 2 branches that are both 12 out of 64. Add them together and you get 24 out of 64. And the probability of both green, that's 6 out of 8 times 6 out of 8, which is 36 out of 64. So one dice you could get a 1, 2, 3, 4, 5, and 6. The other dice, same thing. And what we're looking at here, our X is the difference between the higher score and the lower score. So what's going to happen is any time that your dice are the same number, there's going to be no difference. They'll all be zeros. But 2 and a 1, the difference is 1. 3 and a 1, difference is 2. So now our big X is the difference between the two. You could get a difference of 0, a difference of 1, a difference of 2, a difference of 3, a difference of 4, and a difference of 5. What are your chances of getting a difference of 0? Well, if we add them all up, 6 out of 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 ones, 8 twos, 6 threes, 4 fours, and only 2 fives. And again, if you add them all up, it equals 36 out of 36, which is 1. So how's the notation going? Getting used to the big X equals little x and what it means? So your big X is just what you're looking for. Then you list all the possibilities across the top. You could get 0, 1, 2, 3. And usually your big X is the number of times. So usually the numbers across the top go 0, 1, 2, 3. That's generally what happens. Is this a probability distribution? How can you tell? Some people say no. What's wrong? Doesn't add up to 1. If we add these all up here, 0.6 plus 0.5, we get 1.1. No. It's not a probability distribution. Because they do not add up to 1. Here we got a random variable x. We don't even know what it's standing for. And we've got our probability x equals 0 equals a, probability x equals 1 equals 2a, and probability x equals 2 equals 3a. So we set up our probability distribution. We've got x, and the probability big X equals little x there. They're telling us that 0, 1, and 2, right here, here, and here, they're telling us what are the different possibilities. You could get 0, you could get 1, you could get 2 of whatever big X is, even though we don't know what it stands for. And the probability of it equaling 0 is A. Probability equals 1 is 2A. And the probability it equals 2 is 3A. So we need to find out A. How can we set up an equation or something to figure that out? So again, what do all those have to add up to? 1. So if we take A plus 2A plus 3A equals 1, we find out that A has to be 1/6. The branches I imagined, while you could get, if the probability of big X is the number of white cubes, getting no white cubes would be red and then red. And that would be 4 out of 9 first, and then since it's not replaced, 3 out of 8 next. So we get 12 out of 72 for none of them. Probability of getting one white one could have either been white and then red or red and then white. Again, I like drawing the tree diagram because it just is easy to see. But if you wanted to just do the probabilities, you could. And adding those two cases up, you'll get 40 out of 72. And finally, the probability of getting 2, that's white and then white again, is 20 out of 72. Once again, they all add up to 100%. So here's our last one for you to try. They got pretty good chances of getting a job. So here are the results without the tree diagram. So big X is the number of successful attempts. So if they both fail, 5% chance of LOP for everyone, for them both. And one of them would be those two cases, 35% chance, and a 60% chance of happily ever after. What a positive example.